Right. So hello, everyone, and welcome to this presentation, which will be about digital twins for security automation. My name is Kim, and this is joint work together with Professor Stadler at KTH. So we consider the following use case. We assume that we have an IT infrastructure that you see here to the right. And this infrastructure consists of a set of connected components that jointly provide services to a client population. The infrastructure is managed or operated by an organization, which we in this context refer to as the defender. The defender can defend the infrastructure by a combination of monitoring the network to detect possible attacks and also actively taking decisions to respond to ongoing attacks. In addition, there is an attacker that seeks to intrude on the infrastructure and wants to compromise specific components. To achieve this, the attacker uses reconnaissance to gather information and discover vulnerabilities, and then it has to exploit those vulnerabilities in order to gain access. We study this use case from the defender's perspective down here. So we are interested in finding automated strategies that the defender can use to respond to intrusions in real time as they occur. And to this end, we have developed a general framework that can be understood on a high level through the picture that you see here. And this framework centers around a digital twin that you see in the middle. The starting point is that we have a target infrastructure, and this simply corresponds to the infrastructure where we want our defender strategies to be operational in the end. The first thing that we do then is that we take the configuration of this infrastructure and we emulate that to create a digital twin, namely a virtual replica of the real system. We then use the digital twin to run experiments, to evaluate strategies, and to collect data. This data we then use to perform system identification and to identify a formal mathematical model of the system that we can use to optimize defender strategies. This may be, for example, a Markov decision process, or a game, or a dynamical system of some sort. Then, given that mathematical model, we then apply numerical methods, for example, reinforcement learning, game theory, or dynamic programming, to compute optimal or near optimal defender strategies. We then take the computed strategies and we evaluate them in the digital twin. And if this evaluation is deemed successful, we may also implement the strategies in the target infrastructure. So that is our overall framework on a high level. And in the remainder of this presentation, I will go into details. I will talk about in much more detail how we implement these arrows that you see here. And I will do this bottom up. So I'm going to start with the first arrow that we have down here and how we go from the target infrastructure to the digital twin. The input to our framework for creating a digital twin is a configuration file that defines the target infrastructure. And this file includes everything from the components of the infrastructure, the topology that they are connected in, the services, the vulnerabilities, the operating systems, the users, etc. And we can think about the set of all possible configurations that our framework supports as defining a sort of configuration space. And then any digital twin that we create with our framework corresponds to a specific point in this space. Throughout this presentation, I will focus on a specific configuration, just to give an example. And this configuration is shown here. So this infrastructure consists of 33 components that are connected in a topology that you see to the right. And these components run various network services. They run web services, databases, management services, and so on, which are then consumed by the clients that you see on the top here. Further, a subset of the components have vulnerabilities that may be exploited by the attacker. So the first step in creating a digital twin of this infrastructure is that we have to emulate the physical components. So we have to emulate the application servers, the gateway, and the switches. And we do this using Docker containers. So we map each physical component to a container. And then inside that container, we run software to represent the configuration of the component. So to implement the services, the user accounts, the vulnerabilities, and so on. So this means that for this target infrastructure then that has 33 components, we will create 33 different containers. And once we've created these containers, the next step is to emulate their connectivity in how they can communicate. And we do this using virtual networking. So on each of the physical nodes where we're going to run the digital twin, we create virtual networks, subnetworks, using network namespaces. And then we attach the containers to those virtual networks. And then we connect all of the virtual networks on the different management nodes in an overlay network using VXLAN tunnels. So essentially, we obtain an overlay network, which is the network of the digital twin, where the containers can communicate, that is running on top of the substrate network, which usually is an IP network. The next step is that we also want to make sure that this network that we create, this overlay, as closely as possible resembles the network of the real target infrastructure. And we achieve this using the netdem module in the Linux kernel, which allows us to shape the traffic conditions on every virtual network interface card. So this allows us to configure things like delay, bit rates, packet loss, packet reorderings, and jitter, and so on. In our case, we typically use it to configure the internal connections between nodes inside the infrastructure as gigabit connections without packet loss. And then we emulate the external connections between the gateway and the attacker and the clients using 100 megabit connections with some packet loss. And these numbers are drawn from previous empirical studies on enterprise networks. Next, we want to emulate also the switches in the network. And a switch is just a physical component like the others, so they are also emulated with containers. The only difference is that in the switches, we run the Open vSwitch daemon, which allows us to configure the switch remotely using the OpenFlow protocol. Finally, we don't just want our digital twin to be a static replica of the real system. We want it to be dynamic and represent the actors that operate in the real target infrastructure. So this means that we have to emulate the clients, we have to emulate the attacker, and we have to emulate the defender. Starting with the clients, so we emulate the arrivals of the clients from this population using a Poisson process. So at every time step, we sample the number of new clients from this process, and then we emulate the interactions between the clients and the different components and the services using load generators that make requests. To emulate the attacker, we utilize open source pen testing tools like Nmap for scanning and also Metasploit for running automated exploits against the different servers. And finally, to emulate the defender actions, we have developed a custom gRPC API that allows us to run the defender actions. So typical defender actions may be, for example, to create a honeypot or reset the user certificates or migrate a node from one zone to another, or perhaps shut down a node. And we can do all of these actions through this specific gRPC API that we have developed. And this essentially allows us to run these war games between the attacker and the defender in the digital twin, and then study how well different defender strategies work against different types of attackers. So that concludes the first part of this presentation in how we create the digital twin from the target infrastructure. The next part of the presentation will be about how this digital twin now enables a lot of interesting optimization and analysis that we can use. In particular, we will see how we can use the data from the digital twin to identify system models, formal models, that we can optimize to obtain very effective defender strategies. So to collect the data from the digital twin, we have a monitoring system where on each of the emulated devices, so on the containers, we run monitoring agents. And these agents, they scrape log files, they collect events, metrics, and other performance measures of the node, and they push all of that data to an event bus that we have implemented with Kafka. And the data in this bus is then consumed by data pipelines that process the data and write it to storage systems, both for historical data aggregation, but also for real-time decision-making. And using this monitoring setup, we are able to collect hundreds of metrics for every node in real time. and use that to make decisions. One way that we use this data that we collect is that we use it to estimate parameters and distributions of metrics that we need in order to optimize defender strategies. So here you have just one example where I've estimated the distribution of IDS alerts during intrusion, which is seen in blue, and during normal operation, which is seen in red. And I've estimated them using Gaussian mixture models in this case. And once we have estimated all of these distributions that we need and the parameters, we can then use them to formulate an optimization problem of finding the optimal defender strategies. And in our case, the system model that we use for doing this is a discrete time dynamical Markovian system. And we have looked at essentially two variants of this system. So in some part of our work, we assume that the attacker follows a static strategy. And then this corresponds to a partially observed Markov decision process. Whereas in other parts of our work, we assume that the attacker may be strategic and dynamic, and then we rather have a game. But in both cases, the operation is very similar. So you see it on the figure here. We have a Markovian system that has a state, a Markov state, and this state evolves according to a Markovian transition operator. The state, however, is hidden from the defender. So the defender can only observe observations and noisy measurements of the state. So these observations are correlated with the state, but they do not give the full information. So therefore, we process these observations with a filter that gives us a belief state. And this is just a probability distribution over the state space and tells us how likely it is that the system is currently in a certain state based on the observations. And that belief is then input to the controller, or the defender in this case, that will select the next action. And our goal here is to optimize this controller to select the optimal actions to respond to possible intrusions. And here are some results where we have done this. We've optimized the defender controller using reinforcement learning. And you can focus here on the leftmost plot, which is the most interesting and most relevant. On the y-axis here, you have the reward, and on the x-axis, you have the time steps. And in red and blue, you see the performance of our method, and in purple and orange, you see the performance of the baselines. The first thing that we can note is that our method converges to very near optimal performance, which is shown here by the dashed black line, which gives an upper bound. Second, we note that our method greatly outperforms the baselines on all metrics. And third, and I would say the most important thing to note here, is that the performance of our method in simulation, which you see in red, and the performance in the digital twin, which you see in blue, are very close. And this is a receipt sort of indicating that our framework is really working. So if we go back to this figure that we saw previously, we are actually optimizing the defender strategies in this simulation environment here. And then we evaluate them in the digital twin here. And what we observe is that the performance of our learned strategies that we have here is very similar to the one that we have here, which indicates that this system identification step is really working and that this simulation is capturing the important properties of the real digital twin. Now, this was really just a glimpse of our reinforcement learning evaluation. And if you're interested in more details about the algorithms and about the theory and about the system models that we are using here, I refer you to our previous publications on this topic, which are really devoted exactly to this topic on the reinforcement learning part, as opposed to this paper I'm talking about today, which is more focused about the digital twin. But if you're interested in more about the reinforcement learning side, feel free to check out these references and also to approach me, and I'm happy to discuss it. So to conclude this presentation, we develop a framework for automated security, and this framework centers around the digital twin. This is the key enabling technology in our framework that allows us to collect data, to evaluate defender strategies in a realistic environment, and to optimize defender strategies based on real data. And we have shown that we can use this framework to learn optimal defender strategies using reinforcement learning, and that we can outperform current security systems like the snort intrusion prevention system, for example. If you're interested in more details about this framework, then you're very happy to check out documentation. You can find the link down here. And otherwise, I thank you very much for your attention, and I hope to see you at the conference. Thank you.